Alright, time for another DraftPhysics.com video presentation. Seen there on DraftPhysics.com, also on DebatePhysics.com, are 12 or 14 videos, 5 minutes long, going through all the different aspects of where the kinetic energy theorem, which is sort of related to the work energy theorem, frankly, is just contrived. It's made up. It's not a good idea. It doesn't get to the truth. So the mindless marbles, as I'll clean up some of the comments on the last video regarding the lever experiment that Dr. Michael Coop did, proving that science is shit. That scientists really don't care about thinking about what they're doing, and appreciating how careful you have to be about recognizing variables and what you have to control in an experiment. They're just slobs, and so because they're not operating on patience. It's not like the thing's going to die if they do it wrong. So they can get away with this sloppy work, frankly. So anyway, Mindless Marbles left a comment that I hadn't addressed yet, so I figure I'll get to it. So he starts off, I have some bad news for you. So he's talking to Basin Bass. Springs do conserve energy. So whatever. So he means kinetic energy. Well, they have to conserve one or the other. Can't conserve both. And I certainly would argue that no, they do conserve momentum, not kinetic energy. Believe it or not. And the one mass, one radius versus one mass, one radius case, that is the putting the same weight on the same distance on a lever, it's the same weight. They balance. It's the same thing. And so you put energy in one side, you expect to get the energy out the other side, the momentum. And did manage to get most of the energy. So we're talking really about the momentum. And because it's the same mass, obviously there's not a kinetic energy transfer problem. It's only when you have different masses and different velocities that you end up with a kinetic energy problem. And still you lose more kinetic energy than you do momentum, whenever you do have a loss in velocity. Less velocity will mean less kinetic energy because it's a squared function. All right, blah, 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 blah. So he says most of the energy or absolute value of momentum is conserved. So yes, it's not a hard elastic collision because he said he couldn't get the bolts in front to stick reliably. So that's just more talk. He didn't film it, so we can't see that problem. And he stated, which doesn't make any sense, that he got results that were the same as the spring. So that would be reliably. So it doesn't make any sense. So what you're defending is nonsense. It's not what he said. But the springs still satisfy DS criteria of the one mass, one radius, blah, 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 mostly conserving energy. I say it conserves momentum. Yes. Conserves the MV. And yeah, so within 90%. So nowhere in your statement here are you conceding that physicist Michael predicted completely inaccurately. Way off. His model failed to predict the outcome of that simple experiment correctly. That rudimentary one, that basic one of just putting energy on one side and see if you can get the energy out the other side. He said you couldn't do it, and he did it. And you're not even conceding. Moreover, Michael has been saying for a while now that he wanted to do both elastic and inelastic cases. Well, again, and I've been saying for 2 years, what the fuck would inelastic have to do with it? Why would I bother with inelastic in any other circumstance than sticky inelastic, which is the same as elastic, frankly, if nothing deforms. So it's really just saying an experiment where you don't bend any fenders, or an experiment where you bang things in and the things have to carry the energy out. The energy can't go anywhere else but back into the things that crashed into each other. So the whole words inelastic and elastic really don't mean anything, because inelastic can mean very elastic, steel ball, but you put a little bit of Velcro on it, which is why he used the clay. Well, again, it was already stated that that's just insane, in the sense that that's a deformable, and that's worse than just inelastic. Okay, but again, you can just ignore those parts of the video. It seems you're ignoring them. You're describing a part of the video where he got the prediction completely wrong, your theory didn't work, and you're not taking any responsibility for that at all, just ignoring it. So, let me just go over it. The extension of this comment would be, okay, the difference the spring makes and why there is a difference. Why the spring fit my model in one case and didn't fit in the other case, and vice versa. Why their model fit in one case and didn't fit in the other case. So we'll do that. Alright, so as I stated previously in a video, made it clearish, the whole point of finding out how much energy is lost is to be able to use that information in some constructive way. Let's see where this is on the board so I can move the camera appropriately. Alright, so this is the simple case. Same mass on both sides, and all you're really saying is that I'm going to give this extra energy, and my expectation is that I get all of the extra energy back. Now, I can't get all of it back because the lever has a mass, and in the horizontal position, I'm going to have to move the lever. I'm going to have to use some of the energy to cause motion in the lever, so it's going to take something. So in this case, it took 10%. So the lever consumed 10, you could say. If we put 100 in, we get 90 out, and we lose 10 to the lever. And so, yes, there is a spring on here. So technically, right, it's super elastic. But super elastic means that now you have the potential, you're creating the potential for a reflection. That is, if the energy can't be put in, well, it really doesn't matter, because frankly, the only difference is whether there's something that can consume the energy without moving. Then there's nothing in here that can consume the energy without moving, like denting or breaking. There's nothing broken, there's nothing dentable. So that's the difference. So it's all elastic. Alright, so the simple truth is he predicted this would be, 100 in, you'd get 50 back this way. Now he got 0.02 or something. He did get a tiny, 1% did go back. But it's so trivial that it's not even worth mentioning, frankly. And he predicted 50%, and only 50% on this side. So his prediction was way off. Alright, well, the problem with this is as I pointed out, this 10%, you have to account for that. Now, when he did the spring, so let's do the next experiment where he did, okay, you have the 2 mass here, and you have a 1 mass out here. Now, they weigh the same, they balance, so their weight, moving weight, is the same. Pushing weight, if you want to call it that. Alright, and again, we do have a spring here. Okay, and in this case, okay, you would expect that, yes, you put the energy in, and you'd get all the energy out here. Alright, and you don't. So it doesn't come out 90% here. You don't get the 90. Okay, so you put 100 in again, and you're expecting to get 200 out, because all you're going to really do is you have half the mass, but you have twice the velocity. So you've doubled the velocity and half the mass, same amount of momentum. And so you're expecting to get the momentum here. But the problem is as I pointed out, 10% of the energy is going into the lever. So you know that at least 10%. Now, it should be rather consistent, frankly, because you're putting the same amount of energy in. So you'd expect the lever to steal the same amount. But the problem is if you don't have this in the right location, it can't absorb the energy. So you could sort of understand that if I move this in a little bit, it gets lighter, and the fact is it won't move as much. The velocity of the lever here is different than the velocity out here, right? There's a difference in that velocity. So the maximum velocity this can get is less. So even though the object could be pushed faster, you're not going to be able to push it faster. You're only going to get 80%, okay, or some lesser number. And so now obviously either the lever has to keep it, or it has to go into lever loss. Let's call lever loss. It either increases that 10%, okay, to some higher number, or you get a reflection. So that's what really happened in the experiment, is because he didn't account for the fact that there's less energy, and you did in fact need to move it in. Now if you move it out, it gets heavier. So you can sort of understand why I can't push it when it's heavier. So that's like it's too heavy. It has to be moved slower because you're not pushing at the right speed. That is, your deceleration here isn't going to match the acceleration here. It can't accelerate it that fast because it's got it heavier the further out I put it. So then again, you understand that you're going to get a reflection. So you're going to get a reflection if you're too far in or if you're too far out. The necessary consequence is the reflection. And the reflection was the whole thing I talked about trying to avoid. You're trying to create you're trying to do the experiment, and you're trying to minimize the reflection because that will maximize the transfer. So I said in a video previous to him doing the experiment that you might have to adjust this position based on the fact that you do have losses to the lever, and this won't be able to move at twice this speed because the force won't be getting to it. All the force won't be getting there. So it won't be able to move at that speed. So you have to move it at a lesser speed. You have to place it on the lever in the right location for the speed you're expecting. So anyway, the fact is, in his charts, when he has these little lumps, and he got this and this, this is the reflection here. Okay, this is the going out on this side over here, and this is the coming in. If you do just take this number and say, okay, this is twice the mass, so I double that velocity and I add it to here, it would have come out correct. Okay, minus the losses again. And the trick was that his losses got higher. So when he did this experiment, it was only 10% lost to the lever. When he did this experiment, it went up to 20%. So 20% of the momentum didn't get into any, it was neither in the reflection or in this. So neither one of these objects leaving, they were short 20% of the original momentum. So that's something else to consider, that in this circumstance, if that 20% were added to this, okay, it would have been twice the velocity. So there wasn't like this proved any theory, because frankly, okay, you can understand this is a variable that needed to be controlled. This is called a variable in the experiment, this position. And you can't just say mathematically it's twice, because you have to concede that this force going in is not the same force. It's only 90% of what you thought it was, because the lever is going to consume part of that energy, part of that velocity. Part of this one's deceleration is going to get consumed by the lever. Therefore, you have to compensate and make this lighter by moving it in a little bit. And then you'll reduce this reflection and maximize the conversion of the energy. Now that is a little bit complicated. I mean, it shouldn't really slow down, people doing integrals and all kinds of fancy math. It shouldn't really confuse them too much. They should be able to get the idea that, yeah, if this deceleration is being altered by the fact that it has to move a lever, this matter, that it can't possibly put the 100% of the energy into this object, and if it's less than 100%, it does have to be at a different location. Alright, so that deals with mindless marbles. So frankly, I mean, you know, he didn't show real numbers in terms of, you know, pointing out here's the momentum going in, here's the kinetic energy going in, here's the momentum coming out, here's the kinetic energy coming out. So, you know, but if you do that, you can see that, yeah, all you really have to do is take the reflection and put it as a, you know, when he's using a 1 to 2, twice the velocity, and then in the case of 3 mass, that would be 3 times the velocity. And if you do, just add that extra that you got in a reflection, and then realize that you're also missing 20% that you lost, that you didn't conserve that momentum, then you can understand that you can get your 2 to 1 or 3 to 1 relationship in terms of the velocities. All right. So it was far from a proof of his theory. First, he got the elemental thing wrong. You know, same mass in, same mass out, completely wrong prediction. And then the rest of the predictions weren't that close. And he had this weird factor where he started getting increases in the losses to the lever. All right. So now we'll go to other comments and such. Alright, so this is the last comment by Bass and Bass to physicist Michael. No, I'm not saying your numbers don't match, with the exception of the half-mass collision prediction, which didn't come out your way. So the one mass on the equal masses on both sides of the lever at equal distance, and you're just trying to transfer as much of the momentum as possible from one side to the other. He got that prediction wrong. Plainly, flatly. But that's why the angular momentum matters how. So that's because, he says, clearly nobody could honestly say, I don't think there's a single player in this game who could honestly say anyone thought of or cared about anything called angular momentum when it comes to just figuring out how much energy goes in and how much energy comes out. That's really all that's really interesting to anybody. That's all we want to know. That's all anybody who wants to figure out how levers work, that's what they care about. How much of the energy you put in comes out, and where does it come out? This side or that side? That's all that was interesting. Okay. You didn't answer my question, but I asked, wasn't the point of the experiment to see how much energy leaves the carts, leaves with the carts carrying away the energy? Clearly, that's all anybody really wanted to know. All right. Are you going to just ignore the point that the hard elastic collision is different than the clay collision? So again, the very fact that we have to qualify elasticity is a problem. And the real distinction should be the difference between something that is permanently changed, altered, and things that store energy and give it back. And so elastic is things that give back the energy or take all of it. Things where the things that go in are the only things that can move out. That real things have to move. You can't bend or distort or break something and use the energy. I mean, again, it's just a real broken word, because sticky elastic is the same as elastic. It just requires that the energy has to stay in the objects that went in. Okay, or a spring collision. Why did you not demonstrate this case if you're going to conserve angular momentum? So again, and he's not measuring angular momentum of the object. He was measuring the angular momentum of the lever. which again, I don't know why anybody is, I don't know why that's just being ignored. As why wouldn't you ask the question, how is the leftover motion, the momentum, the energy left in the lever, that is the lever's movement after both objects have left the lever, how could that be of any interest beyond just measuring how much waste it accounts for? That's how much you lost. That's how much you know you didn't get into either one of the objects. Whatever amount the lever is moving after the objects leave is just telling you how much energy you didn't get into either one of them. How is that valuable? You can figure out the losses by just measuring how much energy is missing, or momentum. So, anyway, I thought this was ultimately supposed to be comparing KE to MV, not about seeing if angular momentum is conserved. And again, it's saying angular momentum is conserved when you're forcing the cars to move on a linear track, again, doesn't make any sense. They don't have angular momentum. They're moving on a linear track. They're being forced to move linearly. There's no angular momentum for the objects. Is conserved, then this is just a separate experiment. No, it's a distorted experiment. It's a perverted experiment. It's a contrived experiment. It's deliberately intended not to do what was the point, and it's deliberately broken in ways that make it impossible for it to do what it would do if he did it right. It was a deliberate effort to evade the real experiment. Pretend this has something to do with it when, as you're stating, it's a separate experiment. But it's contrived to appear like it's supposed to have something to do with the original experiment described. Alright, so physicist Michael say, the point of the experiment was to determine which model accurately predicts the behavior of the lever system. See, he's pretending that he understands that principle, that point, but that's not what he did, because clearly he didn't do experiments that could make that determination. The experiment that would make that determination is the hard elastic experiment that he didn't do. Okay, the angular momentum does that. So that's just silly. Measuring how much motion is left in the lever doesn't help. Since we've demonstrated, unless you're going to use it sensibly to adjust where you're going to place these objects, the fact that you got 20% of the energy left in the lever tells you that you can't have the same distances. Alright, since we've demonstrated that angular momentum is conserved, so again, who's demonstrated what? See, what he's saying is he's implying right there that somehow he measured the angular momentum of the objects leaving when he didn't. And they didn't have any angular momentum because they're on a linear track. So the whole thing is a big pile of crap. I mean, this is just lying, alright, gibberish. Because what does measuring the angular momentum of the lever have to do with measuring the momentum of the carts? They left at a speed faster than the lever was moving. So obviously you're not measuring the cart's momentum. Alright, we can now use that as a tool to determine in part how the lever system will behave. So again, more bullshit. We can see how it will behave if you test it, if you actually do the experiment. But he didn't do the experiment that needed to be done. If I know the angular momentum before, so this is whatever that even means, there's no angular momentum before. Okay, the cart you're moving before is moving on a linear path and it's just going to crash into a lever. So there's no angular momentum before. I know the angular momentum after must match no matter what kind of collision occurs. So again, that's just saying that the momentum must be conserved. And kind of obviously, the whole point of the experiment is to demonstrate that the two things can't be conserved. It's impossible. Either the lever will do the 1.4 thing over here, okay, or it'll do the 2 thing. It'll do one of those two things, and the two things won't be the same momentum or the same kinetic energy. If it conserves momentum, it won't conserve kinetic energy, and if it conserves kinetic energy, it won't conserve momentum. Fact. Anytime you put all of the energy from one object into another object, you are guaranteed, okay, to either destroy the momentum or either destroy the kinetic energy. This still gives us a range of outcomes, whatever that even means. There's no ranges of outcomes. It's science, okay? Once you know the variables, the outcomes are always going to be the same. All right, and that's where conservation of energy, so that's more bullshit talk, right? Because he's talking about conservation of kinetic energy, not energy in Newtonian sense, takes over. Using the springs will get us closer. So why? What exactly do the springs do? Either the springs give back all their energy or they don't. And the only point is whether the springs deter the ability of the one object to create motion in the other object. The fact is the spring is just getting in the way. The spring is going to change the absorption of the energy hitting the lever. So if I put a spring in front of my head and then you throw a bowling ball at it, it's going to be a different effect than if there's no spring. The spring's going to dampen the effect of the bowling ball. It's going to take the energy in, and it's not going to apply the immediate force. It's going to absorb some of the force, and I'm going to feel less pressure because of it. The bowling ball is going to have less of an effect because that storage is going to allow me to take some of the energy and throw it back that way, back at the bowling ball, and instead of me having to absorb all of it. So instead of getting the full measure of the impact, I'm only going to get half the impact, maybe. That's the fact. So the spring just gets in the way. It just tells the lever, fuck you, we're not going to bother with using your dynamics. We're going to delay the pressure. We're going to change how much pressure we're going to apply by placing a spring in the way. And now we're going to guarantee that some of the energy goes back the wrong way. Okay. Get us closer to also conserving kinetic energy. With the clay, we'll lose some Ke. So some Ke is 60%. So that's the joke. You lost 60% of the energy was wasted hitting the clay, making it change its shape. And so you only got 40% of the energy into the lever. So pretty useless. Up to the point where the carts stick together. I don't know what that means. Up to the point where the carts stick together. They don't stick together, they stick to the lever. Which again was never an issue. Because frankly, if you get these distances just right, you don't need anything sticky. All the energy will be consumed out of the bowling ball, and the recipient will get all of it out. Which again, I didn't get the case where they actually stick. And as I stated in the conversation we had twice, I emphasized that if you do the experiment right, they don't need to stick. Sticking won't be an issue. It'll stick all by itself. No glue, no Velcro, no bullshit. Newton's cradles don't need glue. Okay, so that half the speed test was not disproven. So what the hell does that mean? So that half speed test was not disproven. It just wasn't tested to the limit of a completely inelastic collision. Sorry. I mean, the half speed thing was tested and you failed. But regardless. Now he says, regardless, in all these collisions, we showed that angular momentum is conserved. We showed, who's the we? And again, he's not talking about the angular momentum of the carts. So how can somebody say this honestly? We conserved angular momentum when he's not measuring the momentum of the carts. He's measuring the momentum of the energy left in the lever. I mean, how can he get away with this? Frankly, it's just so ridiculously dishonest. To say he measured the angular momentum of the carts leaving when he didn't. And they didn't have any angular momentum because they were on a linear track. So we can now use that as a predictive tool for this kind of system. So again, that's just such a nonsense statement. Measuring how much momentum the lever has left over is going to allow you to predict what side gets what energy? Nonsense. If you want to know more details, check out my right tool for the right job, right lie for the right propaganda. I mean, what the fuck is this? He's selling himself as some sort of good experimentalist when he's just used jargon and nonsense. He's completely misdescribed what the experiment did. He's not accounting for the fact that the clay is a deformable, that it did in fact just absorb energy. I mean, it's just insane that he's using all this gibberish rhetoric to defend an experiment that really has no value. All right. That goes over with different methods are applicable for different kinds of systems. So it's just amazing. Right tool for the right job. And from the very beginning, he broke the experiment. Just fundamentally said, screw it. I'm not going to do it the way you suggested. I'm going to do it my way. Okay, that ensures that what you say will happen won't happen. Your predictions can't be true because I won't allow them to be true. That's what he did, plainly. Alright, linear momentum isn't even close to being conserved in any collision, so that's just hilarious. I mean, it's just hilarious, right? I mean, is there any point in talking to somebody who can say something that's silly? When obviously Newton's cradles, for practical purposes, conserve the momentum. So it's just silly to say it's not conserved in any, collision. Come on. That's just a bullshit statement there. So that's just any, he says, in big letters here. It's just bullshit. And if I collide two hardened steel balls in space, there's going to be a complete conservation. So conservation of linear momentum does not apply to the lever system. So again, the whole point of doing it was to measure linear momentum. I mean, the fact that you are forcing the carts to run on a linear track isn't ideal, but the idea that they're just going a velocity is the only thing that really wants to be detected, and it's a linear velocity. It doesn't matter whether the velocity is on an arc, it just matters what is the velocity. The velocity is a linear number in all intensive purposes. Momentum doesn't care whether it's going on an arc or whether it's going in a straight line. It just matters what's the mass and what's the velocity. So again, this is just more bullshit rhetoric and will not be a reliable method of predicting low levels how levers will behave. So again, just amazing. Of course they will predict. I did predict, and I predicted accurately. You can get 90% of the energy go transfer from one object to the other object. You're saying there's only 10% of the momentum, 90% of it got lost. Obviously, I'm saying that no, 90% of it was conserved because of your direction has something to do with it. All of DF's lever predictions were entirely based on using conservation of linear momentum, yes, with hard objects. Non-deformable hard objects and not springs, and only the magnitudes, which was already demonstrated to not be how conservation of momentum works in any situation. So again, he says the magnitude doesn't matter, whatever that even means, and only the magnitudes. What does that even mean? There's masses and velocities. All you want to know is how much momentum went in, how much momentum came out, how much KE went in, how much KE came out. Again, he keeps perverting something very simple into something that somehow we're not supposed to be looking at the very simple thing. We're supposed to be looking at something else. Bullshit. I mean, just amazing bullshit. As I said, unless you expect a minor change to completely switch how the physics works, well, that's the truth of it, okay? The truth is you have these distances a little bit off, and it's going to matter. And the more off, the more it's going to matter. So you will lose. It will be incapable of doing the transfer. I mean, the more misshapen the quarter is, the less likely it'll work in the vending machine. I mean, it's just a fact. So this statement, is just wrong, because you can expect that in a lot of experiments, precision is required. A little bit off might as well be a lot off. It doesn't take much off to make it completely off. The switch just isn't, it's like you can flip the switch 99% of all the way. Well, it doesn't work. It's not 100%, doesn't turn on. How the physics works at this fundamental, as said, unless you expect a minor change to completely switch how the physics works at a fundamental level. It doesn't switch the physics, it's just an acknowledgement that changes and make changes. You change the variables, you're going to change the outcome. The method that DS was using to make predictions was fundamentally flawed, so nowhere did he prove this. There was nothing fundamentally flawed in any of my predictions or any of my statements, so that's just wrong. He didn't demonstrate that at all, because he didn't do the experiment I predicted for. As stated, I don't have much interest in predicting how much of the energy. Again, I mean, it's probably calculatable to some extent. You could figure out how heavy my head is, and then you could figure out how much connected to my neck, and then you could swing a bowling ball into it and make some kind of prediction, with a spring, about how much the bowling ball is going to reflect and how much my head's going to deflect. But the idea, there was nothing fundamentally flawed in my analysis of what happens in the transfer. And the fact is, you just didn't do the experiment you were required to do to find that. If you would have gotten the distances right, the spring wouldn't matter. That's the statement I'm making. The spring only matters if you have the distances wrong, because then you'll get the reflection. Alright, fundamentally flawed, which is why his predictions were garbage. So again, he says my predictions were garbage when obviously your prediction was garbage. Okay, your initial prediction of the simplest experiment was garbage. You said half the energy comes back as a reflection, nothing came back as a reflection, and 90% of the energy went into the other object, where you said only 50% would get into that object. Your prediction was garbage. Your prediction was garbage. Your prediction was garbage. Your predictions. Yeah. All right. As for actually trying the hard elastic collision, so here's some more lies, right? So he's said it, and now he's going to type it. So we have two versions of the lie to use now. I did try it. Okay. But the practical issue was with attaching the hard bumper to the carts. So there was no practical issue, because he got exactly the results his theory predicts. So you can't have it both ways. You can't say there was some problem doing the experiment because I got exactly what my prediction stated should happen. Does that make any sense? No, that doesn't make any sense. The methods I tried did not result in collisions that were any better, whatever that means. Any better at conserving energy than the springs. What does that mean? It can't mean anything, right? Why were you expecting it to be better? The only way you don't conserve energy is you have losses to the lever. And if you're saying it wasn't any better, well, of course it can't be any better. How can you change the weight of the lever and how much energy the lever is going to consume? So what was the better he was looking for? And they were much harder to set up. So again, this is just talk, right? Doesn't seem like it'd be all that hard to do, frankly. I mean, you take that lump of clay he puts on the front of the cart, right? I mean, I could draw it, but you take the lump of clay and you put it on the front of the cart. And then you stick a bolt in it, you know, with the pointy end down and the round end up. And it just sits above the clay. Well, the clay's not going to move. Clay's not going to deform, because the clay's not going to get hit. The bolt's going to get hit, and it's going to put the energy right into the cart. No problem. So this is all just absolute bullshit. So this is the part where he just shows he's dishonest. Okay, that he's really not going to tell us anything like the truth. So the fact is, he did do the hard elastic. He didn't video it, and he's just lying, in my opinion, about what it did. Because if it did exactly what he predicted, he would have videoed it. And the fact that it didn't do exactly what he predicted, that's why we're not seeing it. So I went to the option that showed similar performance. So this is the amazing part. He was talking about conservation of the energy, and so he went to the option that showed similar performance with less difficulty in the setup. The similar performance is 60% of the energy wasted, lost. How could that be similar performance? So you went from 25% losses to 60%. How is that similar results? I don't know. It doesn't sound like a similar result. I mean, it's just such bullshit. All right. But again, unless you're suggesting that the laws of physics change. So he's talking about the laws of physics as if this experiment was at all fair to analyzing those laws or to getting to the truth of those laws. And it's just such a piece of dishonest crap. I mean, in the past, you know, you could argue that the Chardonnay woman just wasn't smart enough to figure out that denting clay with round objects wouldn't give you the truth. So they made mistakes, okay, in their experiments. But this guy is not stupid enough to make those mistakes. So this is deliberate fakery. I mean, this is just nonsense. For him to tell us with a straight face that he doesn't know that the clay consumed a gigantic portion of the energy, a huge proportion of it. He really doesn't understand that? Can anybody believe that? And that somehow that would show something in the experiment by stealing 60% of the energy, that somehow you do a good job of showing what happens? That this is a good test for the lever, is to steal as much of the energy as possible so it can't get to the lever? So I went with the option that showed similar performance. I don't know what the similar performance was. It was a complete failure. All right, anyway, with less difficulty in the setup. But again, unless you're suggesting that the laws of physics change completely, going from conservation of angular momentum to conserving magnitude of linear momentum. I don't even know why magnitude of linear momentum. Why would somebody put that in there? Total linear momentum might be a good word. Who cares which way the momentum's going, right? So I guess that's why he's using magnitude, is to say irregardless of direction. So you know, the fact that they don't have any right words for this because they've broken the idea of momentum by inventing unmomentum. This idea that somehow you can have motion in a direction that undoes the motion in the other direction, you know, anti-momentum. It's just a nonsense term as far as I'm concerned, and certainly it just breaks language to play this game. But anyway, I guess that's what he's trying to do, is make this distinction that and the point is clear. I just don't know why everybody just can't concede. I mean, do I really have to draw the MV with the square on it and point out that you can't conserve both? That if I change the velocity and increase, you know, if I make a proportional change to the mass, make the mass bigger, and make the velocity less, that I can't conserve both momentum and kinetic energy. I can't do it if I change the mass that holds the energy. All right. And then we would not expect the masses the massive change that would be required. So you would expect it, as stated. I mean, it's not hard to calculate that if the reflection went into the object that's lighter, that it would be twice the velocity, and that you would start conserving the momentum. And the reason why you didn't conserve it is because you created a reflection on purpose. Okay, required for DS predictions to be anywhere close to met. Yeah, they would have been met if you did the experiment correctly and understood your obligations to adjust the variables. But again, if DS or yourself want to test that, yes, we're going to have to. That's the obligation, because you did such a shitty job of it, creating this distorted, perverted piece of garbage science. And so now it has to be fixed, because you're created a lie. You're promoting the lie, and somebody's going to have to correct your lies because you're a liar. Okay, you're welcome to try it yourself. I'd love to see it. Well, I don't think you're going to love it, because frankly it's going to prove you were a liar, that you did fake the experiment, that you didn't do the hard elastic experiment on purpose because it doesn't fit your model and it won't work for you. Okay. Just junk. Alright. Yeah, I don't know if I mean, there's a little jerky comment by the John Sean Walker who posts to a link to, just more of this garbage, that they just invent an idea of angular momentum. And they say that, we're just going to take regular momentum, and then if I move something further out, then I multiply it by 2 and give it kinetic energy. So I just pretend it has it, but they won't show that it has it. They won't test it. So again, it's just them saying that I'm just going to sit there and square, okay, the velocity component by using the distance as the way of squaring it. The double the distance is the same as, pointing out that the velocity is twice as much. So yes, the velocity is twice as much, so you already have velocity in there. And yes, it's completely proportional to the distance. If it's twice the distance, that's why it's twice the velocity. So now you have 2 2's. So you have 2 times 2 or 4, or 3 times 3 is 6. So no matter what numbers you use, you end up with the squared term. But it's a contrivance. Who agreed that that's the formula? I didn't agree to it. Nobody got my vote. Okay, my vote is you just measure the momentum. You don't multiply it. There's nothing that you don't need to multiply. Once you've measured the velocity of something, you're done measuring. There's nothing else to measure. There's nothing else to multiply it by. It doesn't gain any extra merely because you positioned it somewhere. Now you're claiming because it's positioned there, it has 4 times the velocity. No, it doesn't have 4 times the velocity. It only has twice the velocity. Yeah, it's just such contrived crap. Alright, so that might be enough of a video. Yeah, 48 minutes, it's enough. Yeah, so I don't know where we go from here. I figure I guess I'll talk about photons or some other subject for a while, because no one will touch the arguments. I mean, what can I do? So I made a bunch of 5-minute videos on all these individual subjects. They won't respond to any of these videos. They won't respond to the 5-minute videos. Nobody will respond to any of the arguments made in any of these videos. So what's the point? I can't argue with, fuck you, you're wrong. That's not a counter argument. And pretending that this crap experiment proved anything, I mean, that's also a crap argument. We've already proven it. No, you didn't. Not even close. Alright, so not much to say. Till the next time and such, I guess. That's all there is to say. I will endeavor to persevere, but oof. It's a difficult task on a planet covered with fucking dumb monkeys.